Let's now take a look at glass transitions and melting within polymers. So we're familiar with the term melting, right? Materials melt when they lose the order that keeps them a solid, and then they become a liquid. And the same can happen for the crystalline portion of polymers, right? So they have some order, you raise the temperature, they can no longer retain that order with the molecules moving around as fast as they do as you're raising the temperature, and the material, that portion of the material melts. Amorphous materials don't melt because they have no order to begin with. What they have is what's called a glass transition point. So there's a glass transition point below which the polymer's chains don't have enough energy to move past each other very easily. And that makes the material brittle, and that's why it's called glass. So below this point, it's like glass in that it's brittle, and above this point, it's more like the typical soft plastics that we know, or rubbers, where the polymer chains can move past each other fairly easily, and so things are flexible. So in a semi-crystalline polymer, we have both crystalline polymer parts and amorphous polymer parts. And so in those types of materials, you're going to see both a glass transition point, which is where the amorphous portion is changing, and a melting point, which is where the crystalline portion is changing. The melting point is always bigger than the glass transition point. What drives the value for the glass transition point and the melting point is chain mobility, so how easily these chains can move past each other. And this is driven by something called a free volume, which is how much space there are between the polymer chains on the molecular level. So in the next guided inquiry, you're going to take a look at what this chain mobility means and what may govern chain mobility, what makes it easier or harder, and then from that gain insight into what types of polymers may have higher or lower glass transition points and melting points.